So welcome everyone to the pizza seminar of this week. Today the speaker is Enrique Gaztañaga, and he will explain us why we live or why our universe is inside a black hole. So Enrique, whenever you want, you can start with the talk.
Thank you, Ramon. Can you hear me well?
Yes.
Okay, so the main thing I want to try to convince you today, not using general relativity, but just basically regular physics, is that we live in our universe is inside a black hole. That's the main thing. And I will start just explaining what is a black hole. And as an example, I will explain why there are no massive neutron stars. And finally, after I try to convince you that we are inside the black hole, and that's the main take-home message, I will speculate how we end up inside the black hole, okay? And this produce a new model for the start of our universe. So basically, I'm going to present a model that is very similar to the Big Bang, but the beginning is not the same as the Big Bang, okay? So the Big Bang has several fundamental problems that I will mention briefly, and I have discussed more in extent. These are very well known. This is not something I have invented. Everybody knows these problems. One that is very interesting, and I will not discuss, but maybe you can ask questions about this if we have time at the end, is this issue of the low entropy star, or the issue that the universe starts out of nothing. What does this mean? This is a problem. It's a fundamental problem that we don't quite understand. The second problem is inflation. I'm going to tell you that to make structures in the universe, we have this problem that we cannot, with the Big Bang model, we cannot do it. This is called the horizon problem. And therefore, we need to put this kind of exotic ingredient to the beginning of the universe, which is called inflation. And some people think that this is, in fact, the Big Bang, the beginning of everything. But this is not enough. We also need dark matter. Without dark matter, even with inflation, even with a universe that starts out of nothing, you still cannot make galaxies, and you cannot make the structure that we observe. So we need to put this another exotic ingredient, which is dark matter. We have looked for it for 30 years, and we have never found it. We don't know what is the particle or the fundamental structure behind it. We need dark matter for several reasons. I'm not going to talk about this in detail, but that's a very important problem. And finally, we also need dark energy, because we have measured that the universe is expanding in an accelerated way. And we don't have any way to understand that so far, unless we invent this other ingredient that we don't understand, which is dark energy. So you see, we have all these fundamental problems that we don't understand about the model of the universe. And the issue is this hinting to new physics, for example, dark matter physics or dark energy physics or string theory or quantum gravity? Or is this telling us that there is something wrong, fundamentally wrong, or that with this Big Bang model, is with these initial conditions that starting out of nothing? So I'm going to try to convince you of a possible solution to understand this black hole issue in those directions. And I just want to mention that even if the Big Bang model was okay, and everything I said is not a problem, and the Big Bang doesn't explain why we are inside the black hole. It's not in the model. There's nothing there explains that. So that by itself is a problem, even if you believe in the Big Bang. Okay, so what is a black hole? So most of you already know what it is, so I'll go quickly through that. So a black hole can be defined as an object with a radial escape velocity equal the speed of light. And so this is very important. This is basically a consequence of causality. The fact that the speed of light is constant means that that there is a maximum speed you can use to escape from an object that has a given mass, okay? So you can do this energy conservation. This is just Newtonian energy conservation, saying that the escape velocity, the kinetical energy for the escape velocity equals the potential energy of the object. This is the equation for the radial escape velocity. It corresponds to energy equals 0 because you want the velocity to be 0 at infinity, okay? And so this is just Kepler's law. And what this is, if you want these two things to be equal, then we know that R dot cannot be bigger than 1. I'm using units where R dot is the velocity, is the radial velocity, dot means the relative with respect to time, and c is the speed of light. And I will use units of c equals 1 because it's more convenient. But this shouldn't distract you from the fact of what we're talking about. So basically, I'm just using units where basically time and distance can be used in the same units. So the condition that R dot is equal 1, so the critical escape velocity gives you, this equation gives you that the radius of a black hole is 2gm over c squared. So you can see here the 2gm here, and then R dot equals 1, so R equals 2gm. That's it. Okay, that's very simple to understand what a black hole is. This is basically every object that has a mass has an associated event horizon, which is if you compress that mass into a radius, which is we call S for Schwarzschild radius, or sometimes we call event horizon, that's the size of that object will correspond to a black hole. For example, we have a black hole mass associated to our mass. If you compress us to a tiny fraction of an atom, then we will be a black hole, okay? That's what a black hole is. So, well, this has a lot of interesting history. You probably know about this maybe more than me. It's kind of interesting that Einstein didn't believe black hole existed. And I think this is interesting because Einstein was not stupid, and it's difficult to make a black hole, right? Because the minute something has some rotation, then angular momentum will prevent you from making a black hole, because that's why galaxies get flatter, because angular momentum, if you contract something very much, any small angular momentum will be preserved, and you have a very fast rotator. Anyway, so a very interesting thing that a lot of people didn't appreciate, even scientists, is that for a fixed mass, the density of the black hole scales like r to the minus 2 instead of r to the minus 3. And this is key for my presentation, okay? So how do you know that? Well, you say, what is the density of the black hole? It's the mass over the volume. But remember that the mass is proportional to the distance. Therefore, when you put the volume cube, you get r to the minus 2. Why is this important? Okay, here is a black hole. So basically, a black hole means if you take a solar mass and you put it in a kilometer radius, that's a black hole, okay? But you can also have 1,000 solar masses black hole, and then it will be 1,000 kilometers, right? Basically, it's 1-to-1 between kilometers and solar masses, okay? So what happens is that if the mass of the black hole is very large, then the density is very low, right? It goes like it goes like r square, or it goes like the inverse of the mass square. Okay, so a very large black hole has a very low density, and these people always think that the black hole is something that has a lot of density. No, this is a very important a key ingredient to understand that. Okay, so how does a black hole form? So imagine you don't have angular momentum. This is very important. Okay, and that's a key thing for making black holes. Then energy conservation will just tell you how free fall mass infalls. Okay, this is the same equation as before. Energy equals 0, we equate kinetic energy to potential energy. And then we get this. This is the equation for the free fall. So if you have an object with a constant mass, for example, a gas cloud that is collapsing, the rate of collapse, which is this, that's the rate of collapse, depends on the density. The higher the density, the larger the rate, okay? And for a small density, the rate of collapse is very slow, okay? And so the idea is that if you start with a very massive and low density object, if it collapses and nothing stops the collapse, right? No physics stops that collapse, then it will become a black hole, right? So that's how a black hole forms. So an object of a fixed mass collapses, gets smaller and smaller and smaller, the density gets higher and higher, and there is a moment where you hit the black hole, and then I didn't say that, but everybody knows that nothing can escape the black hole. That's the definition, but things can fall in. That's very important. And this is why I put here a dashed line, because it's like a membrane where things can get in, but they cannot get out, okay? Okay. So an interesting thing of this argument that I just made about how a black hole is formed is that we have, in physics, we have this Gauss law. The Gauss law tells us that for a spherical symmetric object, what I described will happen no matter what is outside. Okay, Gauss law protect us from what is outside. The collapse will happen as long as you have a spherical symmetry, for example, a homogeneous background. A star will collapse and form a black hole, unless something stops that. I'm going to talk about that next. No matter what is outside. The outside can be anything. And in general relativity, this is Birkhoff theorem, is the equivalent of Gauss theorem, right? Remember that. So you don't have to have empty space outside to form it. You can have other stuff and you still have it. Okay. Point 2, why there are no massive neutron stars? Okay, look at this plot. This is a diagram I made where I put here density and here I put radius. Density is in solar masses per kilometer cube and radius is in kilometers, okay? Now consider a cloud of dust, of mass, like a hydrogen cloud if you want. It doesn't matter what is inside, the content, that is collapsing. Okay, if it is collapsing, it will follow this rule that we had before. That's the rate of collapse. And basically, because it has a fixed mass, the density, it will follow this line. So the density will go like R to the minus 3. Okay, this is a solar mass cloud. So the only thing I have put here is a solar mass. And then depending, you can start with a very large size, for example, 10 to the 4 kilometers. And as the cloud collapses, it moves in this direction. Okay, this is just Newtonian mechanics. Okay, the density increases with the radius to the cube. Okay, just because the mass is fixed. And that's how you make a star. Okay, you have a gas, a hydrogen cloud that collapses. And why we make a star? Well, because we have Pauli exclusion principle. So we know that there is a saturation of nuclear materials, right? If you look at the nuclear density, there is a maximum value that is called the nuclear saturation and basically corresponds to the Pauli exclusion principle. So neutrons are degenerate because they are fermions and they cannot occupy the same state. Therefore, if you try to put two neutrons together, they exclude each other and there is what is called degeneracy pressure, okay? So here is the density of the neutron stars, of the nuclear saturation is the green line. So if you have one solar mass cloud of hydrogen that collapses, eventually the density will be so high that it will hit this Pauli exclusion principle and it will stop the collapse, okay? And that's how you make a neutron star. Okay, this is a simplified version. In reality, you have to take into account the equation of state, so how the pressure relates to density, but it's pretty much, that's pretty much the picture, right? There are some subtleties here. As I mentioned, there is rotation, there is magnetic fields, there are several things, but this is a cartoon version of how you make a neutron star. Now, why there are no neutron stars with 10 to the 4 solar masses? Here is a 10 to the 4 solar masses gas cloud that is collapsing. You see, what happens is that before you get to the nuclear saturation density, it forms a black hole. And that's why there are no massive neutron stars, basically because you can put the black hole density, and as I told you, the black hole density is basically 1 solar mass per kilometer cube, and it goes like r to the -2. So basically, this is it here, and you can see that there is a point, there is a critical mass where the black hole mass equals the neutron star mass, and that's about 40 solar masses. Now, that's not the maximum mass for a neutron star. It's something more closer to 2 or 3 solar masses. And this is because of what I said of the equation of state when you model this more in detail. But I just want to make this point that inside black holes, there are neutron stars with 10 to the 4 solar masses, because after this cloud makes a black hole, I told you that the density is very low at that stage. So there is nothing preventing the cloud to form a black hole and to proceed inside the black hole and make the neutron star inside the black hole, okay? So neutron stars maybe exist of these such masses, but they are shielded by a black hole. And because we don't see what is inside, then it does not matter what is, basically we cannot see what is inside, right? And I didn't mention this here, but this also makes black hole a very nice candidate for dark matter because they behave like dark matter. They are not interacting with the rest of the matter except except when matter falls in. Okay. Okay, so that's the end of point 2. And now let me go to the main point of the talk, that our universe is in a black hole. So why say that? Okay, remember that the universe is expanding. This was discovered some time ago by Seyfert, Lemaitre, and Hubble. And in fact, we can describe the expansion with the exact same equation that I wrote before. Is basically, you can describe the expansion instead of thinking about the info that I talked before. The same equation also can be used for the expansion. You equate the kinetical energy of the expansion to the potential energy, and then you get the Freeman equation that tells you that the rate of expansion is proportional to the density. This is exactly the same equation we used before, the same as this one, okay? And basically it's telling us what is the rate of expansion as a function of the density. And as you know, we have been able to measure the rate of expansion of the universe using several probes. So we know what h is, and we can also measure the density. So we have seen that this equation is followed by the universe. So it looks like the expansion of the universe is really driven by the density of the universe. Now, why I say that the universe is inside a black hole? Okay, so the first thing you have to notice is that there is this definition, which we call the Hubble horizon, which is just the inverse of the Hubble rate. And this corresponds to a distance, if you use units of c equals 1. And it corresponds to the event horizon of an expanding black hole. Why I say that? If you look at the equation for a black hole that we did use before, it has exactly the same form as the equation for the expansion of the universe if you replace the event horizon by the Hubble horizon. Okay, so in some sense, this looks like a black hole, but it's like an expanding black hole, right? Because it's the Hubble horizon. But the Hubble horizon is a very important quantity because it tells us where causality happens. So anything that is at distances larger than the Hubble horizon are not causally connected. The same thing that happens with a black hole. So there is an analogy here, but it's not exactly a black hole. When the universe becomes a black hole is when we measure cosmic acceleration. And everything we have learned so far about cosmic acceleration, all the different probes, all the concordance, 20 years or maybe more like 30 years of experimental cosmology tell us that in the future, the rate of the expansion will become constant. Okay, and that's the key. If the Hubble horizon becomes constant, then it becomes a black hole. Okay, so in the near future, the universe is accelerating. Basically, this acceleration tends towards a constant, and that constant is by definition a black hole. So right now, the universe is expanding inside this Hubble horizon, but this Hubble horizon is tending to a constant, and that is equivalent to say that we are inside a black hole. Moreover, if instead of using co-moving coordinates, you just go to a rest frame where you are not expanding with the universe, that acceleration in reality looks like a static. So basically, the universe for a rest frame is becoming static. We usually say that it's accelerating, but in reality, it's becoming static. It's accelerating for us because we are moving with the universe, but you can just do a Lorentz contraction, and you can see that that acceleration really corresponds to a static universe. So this is a very well known. Everything I say here, this is not, I mean, you can explain this in general relativity. This is what I did in my last talk in October. You can review that talk to see more technicalities of that. But this is well known. I'm not saying anything strange. It's just saying that the universe is expanding into the de Sitter metric, and de Sitter metric is static, and that's the metric of a black hole from inside. Okay.
Enrique,
yes.
I mean, the inside of the black hole is not static.
Well, ours is. Maybe it depends.
Well, maybe you are using the Schwarzschild solution of general relativity. The interior is not static.
Of course, but this is the Schwarzschild solution is singular. This is not the Schwarzschild solution. This is a new solution. In this solution, the universe tends to be static, and it will be de Sitter inside. And this is a SAC solution to GR. You're talking about the Schwarzschild solution is a singular solution.
But then it's not a black hole.
Well, it's one black hole. A black hole is defined by having an event horizon from outside.
What is inside is not a black hole.
Of course it is.
No?
Anything, I mean, my definition of a black hole is this. A black hole.
Okay, no. If you have a new definition for a black hole, then maybe it's a black hole. But according to the definition of general relativity, it's called a Schwarzschild black hole because it's just a Schwarzschild metric. But there are other metrics that give black holes. And the Freeman-Lemaitre-Robertson-Walker metric gives you a black hole. It gives you a black hole because from outside, you find exactly this. And that's the definition of a black hole. If the definition of a black hole were a Schwarzschild, then people wouldn't call it Schwarzschild. No, the definition of a black hole is much more general, but has a number of conditions for it to be a black hole. I don't think that this satisfies that.
What doesn't satisfy what?
I mean, let me understand. So you have the Sitter matched to what?
To empty space outside.
But Schwarzschild.
See, of course.
And then this is, so what you have is something that is collapsing already inside the horizon, right?
Yeah. This is a formal solution to ER.
Okay, but okay, let's go and see.
Okay, so yes, thank you, in fact, Carlos, for mentioning that, because I didn't say. So usually the first known black hole was Schwarzschild, and that has the problem that the inside is kind of crazy in many ways. One of them is that it's singular. And this black hole that I'm describing here has not such problems. It's just basically a collapsing star. And as I said, Okay, sorry, where I was here. Okay, so anyway, the point is that eventually what we see as the universe is expanding is that it will go into a static situation, and from outside it will look like a black hole. Okay, so this means that you don't need dark energy to explain the acceleration of the universe if you accept that this solution of the black hole is the correct solution. So in what sense the universe is a black hole then? Is a black hole from outside. Okay, from inside, of course, we don't know how a black hole is. And my point, what I want to imagine is that maybe all black holes are like our universe. It's basically a matter expanding or collapsing inside an event horizon. Okay, so let me explain what is the horizon problem, because that's interesting. So it turns out that if you take this solution, which is the Freeman, the expanding or contracted solution that we have used before, then you can see here, if you put rho as a function of mass, you can see here that these are the radius of the expanding mass relates to the Schwarzschild radius and to the Hubble radius in this way. Okay, this just comes from the fact that we are taking 2gm to be the radius of Schwarzschild that we deduced before. So what happens inside the black hole is that you have the Schwarzschild radius, which is this black line. Then you have the collapsing or expanding structure that has a mass m, which is the same as the black hole mass, but is within a radius r. Okay, that radius is expanding or collapsing, and then you also have the horizon that I mentioned before, which was this like kind of like expanding black hole inside, right? Is the causal region. So anything that is in the yellow region here is causally disconnected. Okay, so you have empty space here, the event horizon, and empty space there. Then you have matter, constant density, but only the blue part is causally connected, and the yellow part is causally disconnected, just because it's like the equivalent of a smaller black hole that is moving inside. So the horizon problem, this problem is the same, even if you don't believe in the black hole idea that I just mentioned. In the standard Big Bang, the standard Big Bang model is exactly the same as this. It's the same equations, it's the same thing I described here, okay? The only difference in the standard Big Bang is that this radius r goes to infinity, if you want, and there is no Schwarzschild radius because people haven't thought about that, okay? So what happens then is that because you can see here that this radius expand is lower than the Hubble radius. The Hubble radius expand at a rate that we saw before here, that depends on the density, okay? And this is something we can solve, it's just the Freeman equation. Now, the Hubble radius expands faster than the radius of the cloud. I call this the Freeman-Lemaitre-Robertson-Walker cloud, right? Because it's a finite cloud. And as I mentioned, because of Gauss theorem or Birkhoff's theorem, it doesn't really matter what is outside. This description is correct also for a Freeman universe. So what happens is that because the Hubble radius expands faster than the radius of the object, then is catching up, and all the structure that gets inside our universe, we are inside here in the causal universe, anything that goes inside here comes from regions that we call superhorizon, that have never been in causal contact, okay? And that's called the horizon problem, because all the structures we see in the universe were outside the causal contact in the past, and therefore they could not be created with causality in the Big Bang model. This is how the Big Bang, this is why the Big Bang needs inflation to solve this problem. So in inflation, what happens is that at very high energies in the beginning of the universe, there is this inflation that connects all structures, makes the universe very large and flat. But the problem with inflation is that it also dilutes everything. So you get that with empty space. And therefore, inflation needs a mechanism to stop that dilution and also to get back the matter and radiation that we observe. And this is called reheating. So this is getting, I mean, there are hundreds of models of inflation. There is a whole community working on that, but this has become model dependent and it becomes a bit contrived the first time you hear about it. Once you hear it a few times, then it looks more or less normal. And even if you do all that, you can still not form galaxies because you still need dark matter. And why is that? Because what happens is that when the matter that sees the structure that we see today, for example, galaxies, enter in causal contact, according to the Big Bang, the universe was very hot and dense, and therefore these structures that enter disappear immediately by thermal. So they erase all the structures unless you assume that these structures that enter are not made of baryons, are not made of regular matter, they are made of dark matter. And that's the way, that's the whole picture by which you can make a structure in the Big Bang. Okay, we need dark matter for other things, not only because of that. It comes in several other ways, but that's probably some other topic. So let me explain. Okay, so now my point here is, okay, even if you believe in all this, we now have measured that in the future, we're going to have an event horizon, which is the Sitter universe. And that, as I said, corresponds to the event horizon of the black hole. And this is not explained by the Big Bang, right? And that's why we need the dark energy. But even dark energy has to explain why it has such equation of state that leads you to this static situation at the end. Okay, so what is my proposal of how the universe has ended up inside the black hole? Well, this is go back to that picture that I showed you before, remember? So here I showed the density as a function of radius, and here was a neutron star, which was a solar mass, is the green line. The black line is a 10 to the 4 solar masses black hole, so it forms before you get to nuclear density. And my conjecture is that a bigger cloud of 10 to the 22 solar masses could have collapsed in the past and make a very big black hole, okay? Then, because the density is so low, that cloud collapses inside the black hole and then forms the universe that we see today, okay? Now, the problem with this picture is that that cloud will be collapsing and not expanding, okay? But otherwise, you have all the ingredients to make a universe by just having a cloud of gas that collapses. Okay, but we are expanding. How do I explain that? Okay, so this is the whole picture. So here we have the cloud that collapses. It becomes a black hole when it gets this. So this is a black hole of 10 to the 22 kilometers. The density then is even lower than the density today. So there is no pressure support. So that cloud makes a black hole, keeps collapsing inside, and keeps collapsing for a long time, okay? Until what? Until it gets to the Pauli exclusion principle, right? When you get to neutron degeneracy, you cannot collapse anymore because of neutron degeneracy, and there is a bounce, okay? Why there is a bounce? Well, this is something we need to understand. I think there is a bounce because we are expanding now, so there has to be a bounce, right? But we have never measured stable matter denser than neutron matter. Maybe some of people in the institute, which are not now in the audience, but maybe you could push the neutrons into quarks, and you will have quark degeneracy because they are also fermions. This will make a small difference in the picture, but the idea is that the same way supernova stars explode into supernovas and make neutron stars, my proposal is that there is a big bounce. Now, this is not a 10 to the 22 solar masses star. Why? Because by the time, so here I describe what is going on. So these are numerical solutions to the problem. In fact, the solutions are analytical. Here is the red line is the collapsing cloud, right? We know exactly what is the equation of this collapsing cloud and how much mass there is. And the dashed blue line is the Hubble horizon. So what is the causal horizon? Because there is a causal horizon, which is how long is going to take to be singular, to go to t equals 0. So I put t equals 0 at what we call the Big Bang. So this cloud is collapsing. You can see here is this one, is as it collapses, is getting higher and higher density, okay? And that's the red line. And then the blue line is the time remaining for the collapse that gives you a causal horizon. So what happens here is the opposite of what I described before. So basically, super horizon fluctuations, instead of entering, they exit. So from the causal region here, the fluctuations, the structure, the small scale structure that could be inside that cloud gets outside causal contact, just because R, in this case, when it's collapsing, R goes faster than the causal. And no, sorry. It is because the causal collapse goes faster, right? So then structures go out. You can see here. So the blue region collapses very fast. And so everything that is inside the blue region gets out into the yellow region, which is the super horizon region. Okay, then you have the bounce. What happens is that this time we know exactly what this time is. When this happens, is 10 to the minus 4 seconds to the Big Bang, to the singular situation. The density becomes the density of the neutron star. But at that time, the size of the causal region is that of a solar mass. Okay, so the situation is exactly the same as the one I described for a neutron star. So basically, you have a causal region that is a solar mass causal region that is collapsing and that has the density of the saturation nuclear density. So this is like a synchronized explosion of supernovas or core bounce, right? The neutron, the degeneracy pressure has an elasticity. And of course, this needs to be simulated. So at this stage, if you want, this is a speculation. But I think it's a speculation that makes sense, and that because we see millions of stars exploding in the sky, and that's the mechanism they use to explode, and we have never seen something that is made with higher density, okay? So there is no need for inflation because during the collapse, the perturbations exit the horizon and then re-enter during the expansion. So that's the principle by which we can avoid not only inflation, but also all the high energy Big Bang of the model, right? This happens at giga electron volts. So after that, the universe, after the bounce, the universe expands, and you can have nucleosynthesis, recombination, and then large scale structure formation. Okay, so so that's my idea. That's the thing I want to study. So we need to simulate these bounds to make sure that this makes sense. Is there any other observational evidence out of that? I'm very briefly going to discuss that, and then I finish. So one observational consequence of that is that there cannot be perturbations that are larger than the size R here, right? So basically, any perturbation, once you get inside the black hole, there is no perturbations can be larger than the size of the black hole, or if you want, the size of R. So one thing that you can look is you can look at the CMB, and in the CMB, you can measure the size of perturbations. And when you measure the homogeneity of the CMB. This is a paper we are publishing with Benjamin Camacho. You can see it here. We are finishing the last touches responding to the referee. What happens is that the homogeneity index, which is some measure of how homogeneous is the CMB structure, becomes very flat, close to 0, which means homogeneous at 60 degrees, okay? This is very well known. This was known since COVID. So there is some anomaly in the CMB that there are no structures bigger than 60 degrees on the CMB sky. And it turns out that this 60 degrees corresponds exactly to the size of that. At the CMB, we know what R is. It corresponds to the size of R, of that cloud size. So I take this as evidence that we see homogeneity after that region, because perturbations cannot be larger than that region. We have also studied it with Pablo Fosalva in a paper that is now published, where we look at the cosmological parameters in the CMB as a function of position in the sky, okay? This is something new that has not been done before. And what you can see here is the CMB sky, and in colors, you see the different cosmological parameters as a function of position in the sky. So basically, you have to take a large enough region to be able to measure the cosmological parameters. These cosmological parameters depends mostly on the baryon acoustic oscillations that happen on smaller scales, like 1 degree and smaller scales. And then you can fit, for example, H0 or omega mater or omega lambda as a function of position in the sky. And what we found is that there are regions of the sky that they all have the same cosmological parameters, but those are different from other regions, okay? So it's somehow like there are regions where things look homogeneous and they have some cosmological parameters, and some regions that they are not. And this again agrees very well with this idea that I mentioned before. And this is a way to understand that. So this is the CMB sky. So this is the dashed line, okay? We are in the middle of this sphere. As you look out into the sky, right? The larger the distance, the older the light. So the CMB corresponds to a time in our past, and it corresponds to a sphere, okay? And the Big Bang will also correspond to a sphere that I have put here in red. And this is basically the age of the universe. So it's the distance light travels since the universe begins according to the Big Bang. That's the red sphere here. And what happens is that anything that was the horizon, so the region that light can travel since the beginning of the universe to the CMB time, is a small region. I have exaggerated here this red cone, but this is like 1 degree in the sky. And therefore, is these structures that we see here are super horizon structures, okay? And that the standard model interprets these as structures coming from inflation, okay? But inflation has a scale invariant spectrum, and there should be structures at all scales. There shouldn't be a cutoff in the structures. And we claim that we have measured this in both of these analyses, and that will be one evidence for the model. But there are many, many other things this model predicts that are different. So here is a summary of all of them. So let me very, very briefly go through them. So the expansion law is the same Freeman-Lemaitre-Robertson-Walker metric, is the same solution. The element abundance is given by nucleosynthesis. This is the same in both models. Here is the Big Bang lambda-Coulomb matter explanation. And this is my black hole universe explanation. The cosmic microwave background is also due to recombination, so there's no problem there. Now, the uniformity of the CMB temperature in the Big Bang model is explained by inflation. In the black hole universe, this is explained by the uniform Big Bounce. So the Big Bounce is uniform because the density is always, at a given time, is constant everywhere. So it's synchronized. So basically, every time the density is the same. And that's what makes the universe uniform and not inflation. So there are fluctuations in the CMB that are 10 to the minus 5 in temperature, and we believe that these are the seeds for a structure. And the lambda CDM model predicts or claims that these fluctuations come from inflation, from quantum fluctuations during inflation. But it doesn't predict the amplitude, the 10 to the minus 5. That's not a prediction of inflation. This is a free parameter. So this is one of the most important observables we have in the universe. And we don't have a prediction for it within the Big Bang model. In the black hole universe, this will be related to perturbations at the Big Crunch, right, that happened before. And this can be studied with gravitational instability just from perturbations of gravity. This is something that needs to be studied, and I have to start looking at this to see if we can predict this 10 to the minus 5 from the black hole universe model. It's possible that we can do that, and that would be a genuine prediction without free parameters. Cosmic acceleration is due to dark energy. As I mentioned, in the black hole universe model, this is the black hole event horizon. The age of the universe, 14 gigayears, is again due to dark energy, because without cosmic acceleration, the age of the universe will be different. Here is just given by the mass of the black hole. Just that tells you what is the age of the universe, meaning the age since the universe started expanding. Rotational curves, cosmic flows, this is due to dark matter that we don't know what it is. In the black hole universe, my point is that these are the remnants of the big bounce. So this could be neutron stars or black holes that form when the bounce form. And so this means that there is a new candidate for dark matter, which will be compact neutron stars. Those neutron stars can survive nucleosynthesis and recombination because the universe is expanding very fast. And then it doesn't care if there are neutron stars there. Neutron stars don't have enough attraction to disturb the plasma that there is during nucleosynthesis or recombination. Another observation is the fact that the amount of matter respect to baryons in the universe is 4, right? There is about 4 times more matter in the universe than baryonic matter. There is no explanation for that in the Big Bang model. And I think this could be explained if we simulate the Big Bounce, because it will be the fraction of compact to diffuse remnants. The diffuse remnants will be the baryons that we see in nucleosynthesis and in the recombination, and the compact ones will be the dark matter. There are anomalies in cosmological parameters. Maybe you have heard last pizza seminar, Luis told us about this Hubble tension, that the values of the cosmological parameters are different in different regions of the universe. And this is, we think that this is related to this thing that Pablo found, that the cosmological parameters are different in the CMB. So this could explain the tensions. That the fact that the universe is flat is supposed to be explained by inflation. And I have an argument that says that the universe, because the Minkowski metric is the metric of empty space, we agree on that, because it doesn't make any sense that empty space have a curvature or a topology or a lambda. You know, empty space is empty and should have the Minkowski metric. And general relativity tells us that the matter content doesn't change the topology. The topology is something that you can put there in your metric or that you can measure, but it's not something that is affected by matter. So my argument here is that the universe is flat because it has to be flat. There is no other option. And there is no monopole problem because inflation never happens. So if you don't get to energies of tera electron volts or larger, you don't have monopoles. So you don't need the monopole problem. So in summary, my message is that our universe is inside the black hole. This requires a new model for the start of the universe that solves the lambda-cold matter problems without the need of new physics or the need of quantum gravity. And if you want to read more about this, I have a blog here called Dark Cosmos, where I try to explain this for students and interested readers. And you can also read this preprint, where I summarize everything I have said so far. Okay, and I stop here.
Thank you, Enrique. So